I hope you're already beginning to see some of the power of working with a systematic design process. One piece of that is that you always know what to do next. There's always the next step of the recipe. And that step of the recipe tells you what kind of thing you need to write and where you should be looking to figure out how to write it. So when it's time to write the examples, you know that you can look at the signature and the purpose to help you figure out what the examples need to be. You've also seen the benefit of producing uniformly structured code. Code that's easy for other programmers to read, and code that has an appropriate number of tests. But in this next part, you're going to see the power of systematic design really start to step up. What's going to happen is that because the design method itself, in other words, the meta design in some sense, because the design method itself is structured so that the how to design functions recipe is orthogonal, which is kind of a $10 word for means mostly independent. Because the functions recipe and the data recipe are orthogonal, it means that as we learn more forms of data, the functions recipe is going to continue to work unchanged or mostly unchanged with those forms of data. So now we're going to begin to cover the ground a lot more quickly because of this property of the way the recipes are designed. In week 1, and particularly at the end of week 1, we learned about primitive data, including types like string, number, and image. And we learned the how to design function recipe, and we used it to design functions like double, which consumed a number, and yell, which consumed a string, and area, which consumed a number, and image area, which consumed an image. Now what started to happen this week is we've started to learn about other forms of data, and in particular we've learned about non-primitive data, data where there's a type that we design with the how to design data definitions recipe. And what we did in the last 2 videos was we learned about atomic non-primitive data, and we designed the type city name, and then we designed the best function that consumed a city name. And earlier in the week you actually saw a preview of a form of data called enumerations, which we haven't explicitly covered yet. We'll do that shortly. But you saw another type called traffic light color and a function next color. Now what's going to happen the rest of this week is we're going to learn about some other forms of data, including intervals, enumerations, itemizations, and a special form called distinct. And we'll see examples of those types. And you'll be able to design functions that operate on them. As I said before, the HTDF recipe is largely orthogonal to the form of data. So HTDF works the same way with different forms of data. And what that means in this week is we're going to focus most of the lecture time on designing different kinds of data definitions. And we're going to have to spend much less time on designing functions that consume that data. In some sense, what's happening is we did this little piece of the y-axis, how to design functions, and now we're working out the x-axis. And all this space in the middle, the cross product of the 2 axes, comes very cheaply. We won't have to spend much lecture time talking about these kinds of functions. Instead, we spend most of the lecture time talking about forms of data, and designing these kinds of functions comes almost for free. And what's great is the power of having a design method in which the individual recipes are orthogonal to the form of data is only going to grow from there. Next week, we're mostly going to focus on 2 things. One new form of data, compound data, and also a recipe that helps us design interactive programs like games and animations and things like that. And again, because of this orthogonality, most of the lecture time will be on compound data and on the how to design worlds recipe. And we'll do some examples in the cross product, some examples in the green box, but we won't have to do all of them in lecture, because once you know how to design worlds and once you know compound data, you can do anything in the blue, red, or green boxes. Beyond that, in weeks 4 and 5, when we do lists and trees are complicated structures, but because of this orthogonality, again, they're going to be much easier to learn in this course than they are in some other courses. Orthogonality is always great in design when you can get it. Here you've got orthogonality in the design of the actual design method. And it's giving us some wonderful properties here. We can learn HTDF and HTDW, and we can learn forms of data, and we get the cross product for free. That's going to be a big benefit in terms of using this method. And later on in the course, we'll see some other examples of where we work orthogonality into our own designs and get some similar benefits.